Welcome to part 2 on this video series on relational databases. In this part, we will be talking about design of one single table. Normally, relational database has many tables. Average production commercial database will be having something like few hundred tables, and it's not uncommon to have thousands of tables. And normally your problems start to grow up if you have many tables. However, as we can see in this part, even design of single table can bring some challenges. So there are actually problems which you can see even with one table. So we will start from some practical example, and we will go through all problems which you can face when designing single table and how to solve them. In most of our practical examples and when writing a code, we will use product called SQL Server Express. This is actually a free version of very popular database product, Microsoft SQL Server. This is not the same as SQL Server itself, so it's not the same as paid version. It's so-called light version. It only supports some functionality. It also has limitations in database size, but it will be actually perfect for learning purposes. Just one note about the name of SQL Server. Some people say SQL Server. Other people will pronounce it as SQL Server. Actually, both pronunciations are correct because they both have some historical roots. We will not go into many details of this, but you can simply note that you may hear both SQL Server and SQL Server. So most examples shown in next slides will also work in other relational databases. However, maybe some kind of tweak to syntax may be required, so syntax may be slightly different. And this is because examples will be written on language called SQL. SQL is very important language for relational databases. SQL stands for Structured Query Language. This is one of the oldest database languages, and this is language which is supported by almost every relational database. It's interesting to know that some non-relational database also support SQL, but almost all relational will support it almost for sure. As to other possible relational database products, I need to mention there is a very big variety of relational database products available on the market. This is because, as I already told you before, relational database model is pretty old and classic, and there were so many products developed on this. And the prices for this product range between very expensive products with which cost many $1,000s, sometimes tens of thousands of dollars, and completely free products. There are also many so-called open source products which tends to be free. Actually, SQL Server itself, not SQL Server Express, belongs actually to pretty expensive category. It's not a cheap product at all. Another note, which I also find very important to point it out, that many free products are not really free for everybody. You always need to look at license agreement for your particular product. Many products which are being advertised as free are only free for certain type of use. So probably they would be free for use at home. Often they're free to use for education purposes, but they at the same time may be not free for business use. Or those which are free for business use may be not free for every company. So they may have some limitations in how many people working for company. So for example, if company has less than N people working, in this case, they can use it for free. But if they have more, they need to pay for this. Once again, I'm not going into all this license detail, just wanted to make a note that you always need to read license agreement for particular product you're going to use. And if you want to follow all examples in this lecture, they're guaranteed to work within SQL Server. Whether they work in other products, probably yes, but some kind of adjustment may be necessary. I'm now within the product called Microsoft SQL Server Management Studio, and this is actually visual interface to SQL Server database. Almost all major database products will have some utility which allows you to visually manage, design, and manipulate your database or database objects. We will be using this tool. We will be also learning how to do any manipulation with database using SQL language by writing SQL scripts. So for now, I will show you how to create our first table. I already have a database called Education, which I created to support this lecture, and I will be creating tables in this database. So I go to Tables, I right-click on this, I select New and New Table, and I see dialog actually which allows me to enter column names. I will be creating table employee. So this is actually a table which you have seen on previous screens where we were showing list of employees. So first of all, we need to create ID column. This is, as you remember, our primary key. Data type for this column, we will select it from down, will be integer. And also we need to specify that this is so-called identity column. Identity column in SQL Server means auto-increment column. So our SQL Server will be automatically assigning incremental integer values when we insert records. So the values will be here 1, 2, 3, 4, 5, etc. So in order to specify identity, I go to this dialog, and within is identity drop down, I click yes. Now we also need to have first name. And data type for this will be varchar. Varchar stands for variable character fields, and this 50 means maximum length of this field. We will also create last name. It's also varchar 50. Also we had columns like position, and let it be also varchar 50. And then branch they're working within, and again it will be varchar 50 data type. And finally we have salary. For salary we will have numbers which allow fractional values, so we will select this data type real. So we actually finished entering table column names for this table and specifying the data types. And just a note, this is not perfectly designed table yet, and we will be improving it later, but we just need to start from something. And then we just close this window, and the dialog asks us what table name we want to assign to it. We will call it employee. And click OK. So now if we go to our table section and right-click this section and refresh it, we will see our table just been created. You see, this table employee has been created. And if we expand this table and expand columns, we see it. Let me expand this as well. We see actually columns which we just created there. So we just create our table within SQL Management Studio using user interface. But now I will show you how to do the same using SQL. And it's actually not my purpose to teach you SQL. SQL is pretty big language, and I simply don't have time to show everything SQL has in this lecture. However, I will show you some basic statements which will allow us to run examples. So working with SQL will allow you to reproduce the same on your own computer. And you can use most of the statements in different databases, different from SQL Server as well. Although it's quite possible that your product may have slightly different syntax, there are some dialects of SQL available, so if any of examples do not work, just check your documentation. Maybe you will need to tweak your syntax a little bit. But all examples will certainly work perfectly in SQL Server. So in order to create table using SQL, we are using create table statement, which is currently displayed on the screen. This statement shows table name employee, and list of columns we want to create in our table. So we have column name, and after column name, we type column type. For example, our ID field is integer. First name, last name are variable characters with maximum length of 50. Now, the first column, which we call ID, also has some other fields as well. As you see, it has identity flag, which means that is auto-incremental column. We already learned from previous example what identity column means in SQL Server. And it also marked as primary key. And we also know that we always encourage it to have primary key in our tables. So I just deleted previously created employee table because I cannot create table with the same name. And now I run my statement. I click on execute. It executes. You see this message. It completed successfully. And after that, table has been created. Although in order to show it, I need to click on tables and I need to click on this button to refresh it. So Management Studio will realize new tables. It will realize appearance of new tables. So now we can see employee table here. We can expand it and check that all columns has been created successfully. And once we have successfully created our table, we probably now want to put some data into our table. And in order to do this, we will execute another statement, which is currently shown on the screen. And this is insert statement. This is another SQL statement. And what is shown on the screen is one of the most simple and most basic forms of this statement. This statement has different forms. We will use this basic form. And this form is somewhat self-explanatory. It starts from word insert. After that, we have table name. And now in parentheses, we have list of columns which will be inserting data into. And just note that we have all columns except one. We don't have ID column here in this list. If you look at our columns, we also have ID column. And we omitted it in our list in insert statement. Why we did this? Because this column will be populated automatically. We declared it as identity column, means that SQL Server will insert data automatically, and this will be incremental integer values. Now, after that we have values clause, and within values clause, you see we have series of rows which have some data in parentheses, and each row correspond to a row in the table. So first row is actually will be row in the table which will be inserting data in the same sequence as we listed columns at the beginning of our statement. So once we execute the statement, we will have 5 rows in our employee table. But very often, for practical purposes, you will have another sections in select statement, and another popular part or clause, like they call it in select statement, is where clause. I am currently typing it in. And after where clause, you specify some logical condition which allows you to restrict what records you select from your table. For example, if previously we retrieved entire table, I can put where clause where I would restrict our returned record to the record where branch column has value Milford. So in this case, I will be only retrieving employees who work for Milford branch. So in this case, the statement will look like this. I will execute it. And now you see actually that our resulting table has changed. So now we do not retrieve entire table, but only portion of table. Another very often restriction will be for columns which you return for this section of select statement, for very first section. This form of statement which I presented, where I use star, is actually a very simple form, but not very recommended form. Normally, you will list particular columns which you want to retrieve. For example, you're interested to know only first and last name and position, and you're not interested to know branch and salary. So in this case, you will type in first name. I can use actually help in SQL Server. It's suggesting me what columns are available. It's so-called IntelliSense. So then I will type last name. And we wanted to know position. So I will select position. And I execute this statement. This time you see columns returned are different. And when writing your SQL code, you are actually encouraged always to specify particular column names in select statement instead of specifying star as I did at the very beginning. One benefit of this is obvious. You are transferring less data. You're obviously retrieving only data you need, so you are reducing your data traffic. But there are some other benefits as well, and we will cover them later. Just take it for now that it's much better to specify particular column names. However, within this lecture, I will be using star very often because this is very simple and it will work good for illustration purposes. Now, another important clause in select statement is order by. Let me a little bit restructure my statement. I will not restructure, reformat it, just make it look more structured. And the next clause I wanted to present is order by. And order by, as you can guess, determine at which order your records are returned. Your records could be returned in a certain order. Let me, as I said, for illustration purposes, go back to using star instead of column names. And at this time, I would like to order by last name. So I will execute statement like this. Now I see I have a portion of table returned, portion because I'm only looking for particular branch. And now they order it alphabetically by last name. I can put more than one column in order by statement. For example, I want to order by last name and then first name. That's also possible. In this case, statement will look like this. So you now know the simplest form of select statement. In its simplest form, it will have select, from, where, and order by clauses. All of them are optional. Well, not all of them. The keyword select is not optional, but the rest is actually optional. But probably most typical form of the statement will have these sections, from, where, and order by. And let me just say a few words about this order by section, because there is something which may be not looking very straightforward here. So you obviously understand what order by is doing, it's ordering. But very interesting question, what will happen if we do not have order by? So let me return to previous form of our statement where we do not have it. And in order to do this, I will comment this part. And now you actually see how we can comment one line in SQL. We can just put 2 dashes and it now shown green, which means that it's no longer used. And I will also comment where clause. So I will not longer restrict by certain branch. So we are going back to our original statement, which returns entire table. It's a very interesting question in which order it will return records if we do not specify order by clause. As you can see now on the screen, it's returned it in the same order as we inserted. But as a matter of fact, and this is actually not true only for SQL Server, it's true for all relational databases, it's one of most fundamental facts, the order of records is never maintained. So you never can rely on certain order. You can never expect that your records will be, for example, returned in the order in which they were inserted or in any other particular order unless you specify order by clause. Relational database doesn't maintain order of records. It doesn't guarantee actually that your records will be coming in the same order as they were before, as it can reshuffle your data all the time. So it can actually move data in table, and especially it happens after you did many updates to the table, after you inserted rows, after you deleted rows, after you did many other updates, your record order can be actually different. So this is something to keep in mind. And just another opportunity for me to remind you, I already mentioned it, that it also doesn't maintain number of records. So you cannot say that I want record number 3. But what you can always say and this is actually how you should do it. You can always request record with certain primary key. And I am just going to go ahead and do this. For example, I need record with primary key equal 3. This is Adam Ritchie. In this case, I simply restore my where clause, and instead of branch, I will say ID equal 3. And I execute the statement. Order by is not necessary because I only have one record retrieved. So this is actually the way to request particular record, but you cannot say that I want record number 3. In this particular example, it's just coincidence that record with ID 3 is also happened to the record number 3, but in general, it's never guaranteed to be this way. I already mentioned that all sections or all clauses of select statement are optional. And you have already seen what happens if we remove order by or where clause. If we remove order by, we retrieve in random order. If we remove where, we retrieve all records from table. But you may wonder what happens if we remove from clause as well. So if you don't tell what table to take data from. Actually, as a matter of fact, a select statement can work in this form as well. Let me show you this form. This is another special form of this statement. I am removing everything, including from, and I'm leaving just select keyword alone. And I will remove this star as well. So in select statement, I simply can return some static data. For example, I will return word example. And let me put another word, which I will call another example. Let me execute statement in this form. You can now see in the bottom portion of the screen what has been returned. It just returned some so-called virtual table. So instead of returning data from real table, it created some table on fly. So it's still table, but this table which has only one row and two columns. One is showing example and another is showing another example. And you can actually look here and see that these columns do not have names. Obviously, they don't have names because they didn't come from any particular table. But we can easily fix it. Within select statement, we have syntax like this. We can say S, and we can provide some name for this column. For example, I will call it column A. And our second column will be called column B. And execute it again. So this time, as you can see, you have pretty well-defined table. You have table with two columns, column A and column B, and you have one row in this table. So the main conclusion to take from all these experiments and all examples that select statement is always returning table. So no matter which form you use, it's always returning table. It could be real table like employee table, or it could be some kind of virtual table like table it created on fly, like our last example where we just specified some data within statement itself. You already know from previous part of the lecture that relational databases are all about tables. So you deal with tables very often, and select statement is not exception. It's actually accessing table, and what it returns, it's always coming in the form of some table. So we now have tools to work with tables, and let's go back to our primary concern, which is database design, which is how do we design our tables. Normally, you will have design problems when you have many tables because you have so many of them. Sometimes you will have hundreds, sometimes even more than that, and they will be in some kind of complex relationship with each other. But interesting to know that even with one single table, you already have many design challenges and design considerations. So let's briefly review some of them. The first problem is actually already well known to you. This is problem, do we have duplicates in our table? We already know that good relational design doesn't allow duplicates. And now you see the table which you have already seen before on one of previous slides. It actually shows one possible duplicate. These are records for the person named John Clark. Previously, the design of this table was not acceptable at all because these records were complete duplicates. At this point, it's acceptable because, as you can see, there is a new column on the left, call it ID. This is our primary key, and this primary key eliminates duplication altogether. Primary key is always unique. So if you have primary key in your table, your entire table is free of this duplicate problem by design, because there couldn't be two records with absolutely the same column. At least one of them, which is your primary key, will be always different. However, it's actually not as straightforward as it looks, because this rule of not having duplicate, it doesn't apply to just physical design of the table. So it's not just formal rules that you can formally solve by introducing some artificial unique column. This rule more applies for logical design. Logical design means that even if your records are not physically duplicates, if they have different primary key value, they still could be logically duplicates. They still could be holding the same information. It's maybe not necessarily good design. It's not always effective. However, actually, there are two cases which we will consider. In one of them, it's perfectly fine to have record which differ by just primary key. In other cases, it's not recommended. So the case shown currently on the screen is actually a case where it's perfectly fine to design it like this. And the primary reason for this, records which we currently see, these John Clark records, they are not really duplicates. They only look like duplicate, but they refer to totally different persons. So first John Clark is one man, another John Clark is totally different man. They may not even look similar. It's quite possible that one of them young, for example, and another is old. It's possible that one of them tall and another is small. So these are two different persons. It just happened. It's just kind of coincidence that they have the same name, they have the same occupation, they are both accountant, and they work in the same branch and get the same salary. But introduction of primary key actually sorted our biggest concern here. And biggest concern was actually how to refer to this record. How do we actually distinguish between these two records if we connect this table to some other table? For example, these people could be responsible for some project. And we have another table which holds project data. And this project is supposed to refer to a person who is responsible for it. So one project in this case will store ID of employee 2. So it will refer to the first record of first John Clark. And another project will refer to record with ID 3. In this case, we actually resolve ambiguity between these people, and we do not longer have any problem of duplicate. And another thing to mention, that as I already told you, these records are only coincidentally duplicated. And coincidentally means they only duplicate because we only store some columns, some particular column in this table. Let's add another column to the table. For example, let's add the personal address, the address of residence, and records will be immediately different, or because they have different address, or different phone number, or different email, so there are some differences. Even if we do not add columns, even if we keep our columns the same, at some point they probably will have different salary. So even with current columns, they are not really duplicates. It just happened for them to be duplicates at this particular point. And now let's have a look at another case. In this case, assume we are running some grocery store and we want to store information about items we have on the shelf in our dairy section. And we have milk and we have cream. And you now see some duplicates. You see actually that rows with ID 1 and 2 are absolutely the same. They are not technically duplicates because they have different IDs, they have different primary key, but they are logically duplicates. And unlike previous example with different accountants, these items are really the same. Well, they may be physically different as well, but we do not distinguish between them. It's not important for us which particular bottle of milk it is. So this design is actually bad. We have duplicates here. despite the fact that we have primary key which technically makes them to be different. What would be proper design for this? Proper design for this is shown on the bottom of the screen. The proper design will be to introduce quantity column. So in this case, each row in the table describes kind of item we have on the shelf, and we have quantity which is showing how many of them we have. So this design is obviously better. However, those people who pay much attention to what I am showing may notice that there is something bad in this table as well. And this actually, I'm talking about this column FAT. What is bad with this column? It's actually mixing different kind of data in the same column. It's showing numeric data and measurement unit, which is in this case is percent. So this is pretty bad because normally it should be, you should have only numeric value, and either entire column should be in the same measurement unit, which is percent, or if you have different measurement unit, it should be handled totally differently. You should have reference to these units. Just was a quick note because some people could be disappointed with the fact that I'm saying proper design and at the same time showing something which is not really nice. But when I say proper design, I mean proper design in terms of duplicates. So let's actually handle one problem per time. We cannot really handle them all at the same time. At this time, we are talking about duplicates, and for duplicates, this is actually a perfectly designed table. Another well-known problem, which also can be seen as a design problem of a single table, is problem of repeated groups. Repeated groups are illustrated in the last column of this table. This is column called hobbies. And as you can see, this column contains more than one item. So I mean, records of this column contain more than one item. So for example, for first record, for Sarah Bowden, there are two hobbies, flowers and golf. So people can have two hobbies, one hobby, many hobbies, or don't have any hobbies at all. And this kind of repetition in this column is actually discouraged. So it's actually considered to be pretty bad design. And people with good academic knowledge of this subject, I mean of relational database design, will tell you that this kind of table doesn't comply with so-called first normal form. Normal forms are special rules which are very important for relational databases and which essentially tell you how to build your tables properly, how to avoid mistakes, and how to make your design meticulous. We will be not reviewing all normal forms here because we're simply doing more informal introduction into this subject, and normal forms require a better academic knowledge of this subject. But the existence of normal form is worth mentioning. And it's also worth mentioning that the process of applying these normal forms is known as normalization. There are actually so many things around this normalization. In general, normalization is very good, so it's actually making your design accurate. Sometimes, however, you may have problems when your database is too normalized. There could be problems coming from the fact that it's too difficult, it became too complex, or there could be some performance problems. And this is a very big topic. We're not covering it here. Normalization sometimes can help performance, or it can actually bring performance down. So if this happens, there are some kind of steps which are coming back from normalization, and there is another term for this called denormalization. And very often database designers are struggling between normalization and denormalization. They're trying to find some balance between these two processes. Another problem which we can spot here, and is also from academic view on this relational database design, is the problem of mixing of different cardinality. What is cardinality? Cardinality is actually a term which is coming from set theory, and cardinality stands for how many objects of a certain kind you have. When I say different cardinality, I mean that there are more items in hobbies column than in the rest of the table. For example, the cardinality of first name, last name and position is the same as cardinality of entire table, because every person has only one first name and only one last name, or at least we assume they would have only one of them, and only one position. But person has more than one hobby. So in this case, we would say that cardinality of hobbies is bigger, because it could be more hobbies than persons. So design like the one shown in this screen is generally discouraged. However, there is a question, is it acceptable in general or not? So is it really that bad, or is it sometimes possible to have things like this? Actually, answer to this depends on what you are going to use this information for. I mean, this hobbies information. If the only purpose of this column is just to store this information and probably show it on some screen or maybe print it on some document, then in this case, in general, it's acceptable. It means that you don't actually care about this information. You just need some placeholder where you store some list of hobbies just out of curiosity. You're not going to do anything with this. However, if you want to somehow handle this information, and handle means that probably you want to run some query on this. You're probably building some kind of team of golf players, and you want to find out who is playing golf, who has this hobby. So you want to actually query this table for all employees who have hobbies who have golf in the list of their hobbies. Or you want to somehow order by this. For example, you want to order table by hobbies which people are having. In this case, this design would not be appropriate, because you will have many troubles of writing queries against a column which is designed like this, or in other words, has different cardinality with the table where this column sits on. Now, the problem of choosing proper data type for columns in your table is so common, and mistakes in this could be seen so often, so I can almost guarantee that in every database which you will probably work with or will see, there will be some kind of these problems you probably would be able to identify. One of the most common mistakes is choosing too big data type. I mean data type which is storing more bytes than necessary. And very often you will hear that very often you will see that whenever a column is integer, you have choice of 3 data types. If we are talking about SQL Server, or in other products, they could be named differently, but normally they would also exist. In SQL Server, you have integer, you have small integer, and you have tiny integer. Where integer is 4 bytes, small integer is 2 bytes, and tiny integer is just 1 byte. So, for example, let's say that you are doing database for real estate agency and they store information which describes the real estate properties. And there is a field number of bedrooms. So how many bedrooms it could be? Normally 2, 3, maybe 4, maybe 5 in some cases. But many people will allocate integer for this, which means 4 bytes. 4 bytes maximum value for this column is above 2 billion. So who is going to have 2 billion bedrooms in one house? Now, the next choice, small integer, is also very big because it's 32,000 plus. Again, we are not going to have 32,000. And for tiny integer, the maximum number is 255. This is exactly what we need. We are not going even to approach this number. So obviously, we need to allocate tiny integer which is 1 byte. Allocating proper data type is important in software development in general, not only in databases. However, in databases, it costs more. I mean, mistakes in this cost much more. And this is because if you're running some software product, some program, for example, program on C# or on Java, and you allocated more memory than necessary, then this allocation will last only for very limited time. It will only last when your program works. So when you started your program, you allocated memory. Then when you stop a program, this memory has been released. And if your computer has enough memory, then maybe nobody will ever notice this. So it will not be a big deal at all. Now, in databases, the situation is very different. First of all, we need to take into account that any mistake we make will be multiplied by number of records in our table. So if our table has something like 100 million records, then allocating 1 byte or 4 bytes for certain column will make very big difference because it will actually result in very different space used on hard drive. And another thing which is very important in databases, and again, this is different from just regular software, just from regular program, is that memory allocated in database will last almost forever because databases are kept for a very long time. Sometimes they are kept forever. Sometimes some companies do not erase their records at all because they are valuable. So once you allocated this 4 bytes, this will be 4 bytes forever. It's not like in your program where it can only last few minutes. Another problem is variable length versus fixed length of certain data types. Whenever you actually have information which could be stored as a number, it's better to store it as a number by different reasons. And one of the reasons is actually fixed data type. Numbers always have fixed length. So it's predictable length, it's fixed, and it's always the same. If you store character data, you have choice between at least in SQL Server, these types are called this way, between character and var character. If you remember, when I was creating previous tables in SQL Management Studio, I created them all strings, I declared them as var character, which means variable length. And that was appropriate choice because information stored there was of variable nature. For example, I used it to describe first name and last name. We don't know in advance what is the length of somebody's first name or of somebody's last name. So in this case, variable length is actually a perfect choice, and it's actually the only possible choice because we simply don't have this information. Sometimes you will store different kind of data. For example, you will store some codes. You can store for example, code for some medical procedures, or you can store codes of United States like MA for Massachusetts, CT for Connecticut, NY for New York, and etc. And in this case, you know length of your field. And it's always better to declare them of fixed length if you know the length of the field. Why it's better? Beyond of obvious reasons that it will probably store less information, because in order to maintain variable field you need to store some additional information, what is the current length of your field. It will, but the more important reason is that it will allow you to update records in place. So whenever you update record, you can simply update this value if it is fixed length, you can still update it in place instead of actually relocating entire record. Normally, if you update column with variable length, your database product, SQL Server in this case, will have actually to move this record somewhere because it no longer fits into the space which was previously allocated. So it's actually a much heavier operation. If you update something in place, in this case, there is no need to delete this record and reinsert it somewhere else, no need to reshuffle your data. And there are so many database products available on the market. I cannot guarantee that your particular product you're working with will be always updating data in place, even if they're of fixed length. Your product may be always moving records, so it may be always updating the entire records and never doing this. However, at least when you declare your data type, when you use some data type which has fixed length, at least you allow this product to do it properly. At least you give opportunity to do it, because with variable length columns, it will be always relocation of records, and with fixed time, with fixed size columns, it could be updated in place. Actually, there is one exception. With variable length field, it could also update it in place if your new value has less size than previous value. But this is not necessarily implemented this way. Most of the product will be updating entire record. And another very common problem, what would you choose if you need to store date and time value? You should always choose appropriate type if it is available. For example, in SQL Server, these data types are available. You have types for storing date, you have types for storing type, you can types for storing date and time together. So if you have them available in your product, you should always use them. You should not store your dates as strings, so you should not store them in character form, although it is something which happens very often. Many databases do this. Why is that? Normally, length of this field will be less if it is having appropriate data type, but the most important thing, if it is proper type, for example, date or time type, you can run query against this, and you can actually select records which are after certain date or before certain date or within certain date range. When you use them in character form, it will be way more difficult. You can order by records by date, so present records ordered according to their dates. You can work out difference between dates. For example, you can see that some date is 3 times earlier than other dates. So all these calculations. And finally, if you're using proper date and time types, normally your product will handle daylight savings, which happens in most of the countries. So it will actually handle this case properly. So if you move, for example, from 11 p.m. of the day to the next date when there is a daylight savings, it will add 1 hour, it will take off 1 hour on appropriate dates when necessary. If you store your dates as a string, you will not have access to this service at all. But that was all about database products which do have such types. Some cheaper products, some open source products do not have the concept of date and time. So how would you store date and time there? You have several choices. I think that one of the best choices is store them as integer fields and present them as number of seconds from certain point. In this case, you can still have compare your dates, you can actually work out difference between them. Or as a last resort, you can store them as strings, but in this case, make sure that they're always in the same format and that they're in sortable format, which means that year comes first, then month, and then day. In this case, you also can somehow order them around and compare them. This is end of part 2 of this video series, and you are now invited to watch part 3, which will be devoted to another interesting topic, how we match entities, which means certain classes of objects, to tables. So see you later.